Now let's think about this for just electrons. So only spins, and I have a spin wave function zeta 1, 2. And there are basically four ways I can do this. I can have up, up, down, down, up, down, or down, up. And we call that alpha 1, alpha 2, beta 2, beta 1, beta 2. And those are totally fine, right? Because if I exchange alpha 1 and alpha 2 and it's alpha 1, alpha 2, I get alpha 1 and alpha 2, and it's the same thing. Likewise, beta, beta. So up, up, down, down, no problem. Those are symmetrical with respect to exchange. I get the same wave function back when I do them. But the alpha beta and the beta alpha, that's not so good. So those guys are not the same. Alpha 1 beta 2 is not the same as beta 1 alpha 2. It's a little hard to figure out how they're not the same, but they're not the same thing. And so if you can tell the difference, then they're not the same. So those are not in any way, shape, or form symmetrical, and instead we must properly anti-symmetrize them. And so to symmetrize it, I can make a symmetric zeta wave function by taking 1 over root 2 times alpha 1 beta 2 plus beta 1 alpha 2, the same recipe that we just articulated. And that gets me a symmetrical spin wave function. Likewise, I can get an anti-symmetrical one by taking 1 over root 2 times alpha 1 beta 2 minus beta 1 alpha 2. That's the appropriate recipe for anti-symmetrizing the function. So when we're all done, there are three possible ways to make a symmetrical wave function. I've got the up-up, alpha 1 alpha 2. I've got the 1 over root 2 alpha 1 beta 2 plus beta 1 alpha 2 that's symmetrical, and then I've got the down-down, the beta 1 beta 2. So that is up-up, is total m sub s, z component of plus 1. I've got the up-down, where the m sub z, the z component of the angular momentum, is 0, but it's still, they're kind of aligned-ish, and so they still have a total angular momentum of 1. It's just the 0 z component that I get there, and then I get the down-down, where the total ms is minus 1. All three of those are symmetrical spin exchange wave functions. And then the anti-symmetrical one, the 1/2 1 over root 2 alpha 1 beta 2 minus beta 1 alpha 2, that one corresponds to the exactly anti-aligned case where the total spin angular momentum is 0. Of course, the z component has to be 0, and they are truly, really and truly anti-aligned. So the three cases where I have the zeta symmetrical, we call that a triplet because there's 3 of them. The degeneracy is 3. And the anti-symmetrical single case we call a singlet. We call that the spin degeneracy. How many different ways are there to have the same total value of the spin angular momentum? And if it's 1, it's just, remember g of L is equal to 2 times L plus 1? Well, it's the same darn thing. It's 2 times the total angular momentum quantum number plus 1. So the total angular momentum in the symmetrical case of the spins here, the total spin angular momentum is plus 1, and I've got 3 possibilities. 2 times 1 plus 1 is 3. In the case where I have 0 total spin angular momentum, of course, there's only one way to do it, and I have myself a singlet. Now the last bit here is if the spatial wave functions are identical. In other words, if I have the 2 electrons in the same spatial state, like a 1s1, 1s2, so if I have both Clarissa and Juan in the 1s state, then the spatial wave function is symmetrical with respect to exchange, just like the alpha-alpha or beta-beta cases before. So with the requirement of Pauli that the overall wave function be anti-symmetrical with respect to exchange, there's only one way to do this, and that is to choose the anti-symmetrical spin wave function and perfectly anti-align the electrons. So zeta must be the anti-symmetrical one. And so I have a symmetrical spatial wave function, an anti-symmetrical spin wave function, and I get the appropriate anti-symmetrical wave function. And so it's not just up and down, but it's perfectly anti-aligned spins that give me that case, where the total spin is 0. But the price that I've paid in some sense here is I can no longer tell Clarissa and Juan apart, because if I exchange them, all that happens is the wave function changes sign. So I've mixed some Clarissa character, electron 1, and Juan character, electron 2, into that zeta antisymmetrical singlet spin exchange wave function there, and I can't any longer tell the two electrons apart. And that's just the way it is. So this is that perfect, if I have a 1s2 occupancy with perfect anti-alignment, we also, it's actually a more appropriate thing that I say 1s2. I don't say 1s1, 1s2. I say 1s with two electrons in them, and that's all I get to know. The identity of those two electrons is totally vanished, and that is in fact how it has to be. Now here's something I think is really fun. So now what if the electrons are not in the same spatial wave function? So for example, let's imagine that one of the electrons is in a 1s orbital, and one of the electrons is in a 2s orbital. So we call that configuration 1s1, 2s1, where the 1, the superscript, as you know well, is identifying the fact that there's a single electron in each of those orbitals. And often we're taught to just not even write the 1, but I like to do it because it does the counting explicitly. So that's a little more interesting, because now the spatial wave functions are in fact different. And we have to go through the same business. Now I got to take that spatial wave function and make it appropriately antisymmetrical. So once again, I can either take 1 over root 2 times the sum, positive, of 1s1, 2s2 plus 1s2, 2s1, or I can take 1 over root 2 times 1s1, 2s2 minus 1s2, 2s1. And that is a symmetrical exchange wave function in the spatial coordinates, or an antisymmetrical exchange wave function in the spatial coordinates. All Pauli says is that overall my exchange wave function has to be antisymmetrical for fermions like Clarissa and Juan, or whatever they're called, because we're not allowed to know the difference. And so then I have to multiply that by the opposite kind of spin wave function, right? So in the top one, where I have a symmetrical spatial exchange wave function, that's where I have to invoke the antisymmetrical spin wave function. That's a singlet with the perfectly anti-aligned spins. Or in the other case, where I have an antisymmetrical spatial wave function, then I invoke the symmetrical or triplet spin wave function. So let's think about the spatial exchange here. Basically, remember that incredibly important coordinate, the distance between the two electrons, r12. When I go from, when I invoke the spatial exchange, it's basically equivalent to taking r12 and turning it into minus r12. Because r12 is a vector, it's the distance between the two electrons, and I can point from 1 to 2, and if I turn it around and say, whoops, 1 and 2 have switched signs, I'm basically changing the sign of that vector. And so if I have a symmetrical exchange in this radial part of the wave function, just with respect to the 1, 2, the distance between the two electrons, then if I exchange them, I'm going to get the same function. So r1, 2 is going to be equal to the r, the capital R, the radial wave function, is going to be equal to r2, 1 when I change the coordinate. And if it's antisymmetrical, it's going to change sign. It's going to be the opposite sign. So first let's draw the radial coordinate r12, and let's consider a wave function here. So I've got the wave function this is the distance between the two electrons, and the tick there is at r equals 0. So the first thing is I'm pretty well guaranteed the two electrons are not exactly on top of each other. It's just logically sensible, because the energy would be plus infinity if they were. They hate each other, remember? So we're pretty well guaranteed that the probability of finding r12 equal to 0 is 0. They just won't do that. And there'll be some maximum probable distance between the two electrons, and so the thing will go up to a maximum, and it'll come back down. Obviously there might be nodes in there, etc., etc., etc. This exchange radius coordinate is actually really interesting to theoretical physical chemists. It's quite an important variable, because it really defines that electron correlation stuff that we were talking about. So people really care about it. But the wave function has to look roughly like that. Now in the first case, let's consider the symmetrical exchange wave function. That's kind of the easy one. You just flip the electrons and nothing happens to the wave function. Well, that means that in the negative, it has to look exactly the same. It's just a mirror image, right? I exchange them. I go to negative R12, and that's my nice symmetrical exchange wave function. Well, look at this thing. Take a look near R equals 0. It's got incredibly high curvature. It's got a cusp. The second derivative there is basically infinity. So that thing has enormously high kinetic energy in that part of the wave function. To get the overall kinetic energy of those two electrons, you have to average over the whole wave function and find the appropriate expectation value. But that cusp there is a big deal. And so that basically the way to think about this is for the symmetrical exchange wave function, the two electrons, Clarissa and Juan, hating each other as they do, are really actively working at avoiding each other. And so they have to invoke a lot of kinetic energy when they get too close to each other and actively avoid each other. And so there's a huge amount of kinetic energy around small r12 associated with that cusp there, so they can also maintain the appropriate symmetry that the Pauli principle demands of the situation. And that's really a bummer. It really increases the total kinetic energy of the system. Now, let's consider the antisymmetrical case. So here's R12 again. Here's the same basic wave function in the positive direction of R12. But now, for the antisymmetrical case, it has to change sign on the other side. So I have to flip it over, and it looks like that. That's a nice antisymmetrical wave function. Well, hang on, look at this. Now, in that critical region near R12, remember again, Juan and Clarissa hate each other. So they're trying to avoid each other, so I have to have a very small probability of having them near each other. So the probability of having R12 equals 0 has to be 0. Look at this. It does it perfectly. There's no problem at all. There's no second derivative at all there for low radial coordinates. And so the curvature is 0, and overall, if I average this whole thing over all of those values of R12, I'm going to get a much, much, much lower kinetic energy. And it really is all about that R12 really close to 0 part. Everywhere else, the kinetic energy of those two functions is basically the same. But there's a little area there where there's a huge kinetic energy in the symmetrical case and a very low kinetic energy in the antisymmetrical case. So the antisymmetrical spatial function gets to have lower kinetic energy. And now let's look up there on the top of this graph here, because what I'm saying is the antisymmetrical spatial exchange wave function is lower in energy, lower in total energy, because the electrons have less kinetic energy associated with avoiding each other. They just kind of naturally do it without any problem. They naturally keep their R12 far away from 0. And that one with the antisymmetrical spatial exchange wave function has to be paired with the symmetrical spin exchange wave function, and that happens to have 3 possibilities, so that we call the triplet. The left-hand one with the symmetrical spatial exchange wave function that has the high energy, that one is symmetrical in spatial exchange, and so it has to be paired with the antisymmetrical spin exchange wave function, and that antisymmetrical spin exchange wave function is a singlet. So, all else being equal, if I have different spatial single electron functions, then the case with the antisymmetrical spatial case, spatial wave function, is going to have lower energy than the case with the symmetrical spatial wave function, for the reasons we just described with the curvature. So the triplet wave function has the good spatial part and is lower in energy than the singlet wave function, which has the bad spatial component. But it only works if I can get the singlet and the triplet for the same spatial wave functions. So it only works in a case like this where I have 1s1, 2s1, where I have one electron in a 1s and one electron in a 2s, and then I can mess around with the spatial wave function. So in that case, it's always true that the triplet is lower in energy than the singlet. The triplet is favored when there's a choice. The exception to that is an enormous exception, and that is when I button everything up and I have two electrons in the same orbital, for example the 1s1, then the only possibility is to have the singlet spin, because the spatial exchange wave function is in that the spatial wave function is symmetrical, and I have to have the spin wave function be antisymmetrical. So the ground state with two electrons in, say, a 1s orbital actually does have this sort of purple avoidance energy associated with it. It's icky, but it's still, in the end, the electrons get to be close to the nucleus, and they're willing to pay the penalty, basically. But they do have this high kinetic energy component. It's just they win out in the end. Whereas if I have a 1s1, 2s1 configuration, then the triplet case is lower in energy, and the singlet case is higher in energy for the reasons shown here.